asymptotic. That means R tending to infinity behavior of density for finite systems. And VXC as R tends to infinity. So finite systems and now comment on infinitely large semi-infinite systems, and then the equation for the third equation, although we talk about orbital free DFT, this third equation is not looked at much, and you can relate all the OF DFT to this, but this also makes a connection between the wave functional theories and DFT theories, so I think this is important for the future, so I will spend some time on it. So first I'm going to discuss this part, and that is based on the paper by Amla in 1.1, and I think it is either 1984 or 1985. And this works in terms of quasi-particle amplitudes. Alright, I'll define that, and I'll also comment when I derive this on 124 orbitals. So we have the many-body wave function psi n R1 up to Rn. I'm going to define the quasi-particle amplitude f I as integration psi n minus 1, this I'll take as R of R1 to Rn minus 1, I'm suppressing the spin index. So what you can assume, I'm integrating over all spin indices and the spin index of the nth particle. Psi R1 up to Rn minus 1, Dr1 up to Dr n minus 1. We also integrate over the sigma 1 d sigma 2 all the way to d sigma n. From now on, I'm going to not write this explicitly.
Sir,
yes.
What do you mean by quasi-particle? Is it meaning a particle that is created just above 40 seconds?
No, I'm calling it quasi-particle amplitude because I'm just taking a sort of orbital defined through an overlap between the n minus 1th wave function and nth wave function. So whatever is left, I'm calling an amplitude for the nth particle, and in that sense, it's a quasi-particle. I'm defining an orbital Fi R, which is picking out. You can see that I'm projecting out from this the n minus 1 particle wave function out. So whatever is left sort of can be thought of as the nth particle amplitude left, nth orbital, and this is ith. Okay, I'm just projecting the other thing out. The other way to look at it is I could expand psi n R1 up to Rn as summation Fi R psi n minus 1 Rn R1 up to Rn minus 1, right? I equals 1 through infinity, because this is a complete set. Alright, so in that sense I'm creating a particle somewhere right? These are orbitals. But these are not real orbitals. It's not particle-particle analysis. It's just an amplitude as to there's one particle will form somewhere. In that sense. All right. So once I do that, you can very easily show that the first order density matrix R prime comes out to be summation I Fi R star Fr prime. Again, spin density understood. And density rho R comes out to be summation I, obviously the diagonal term of this, mod Fi R square. So I'm leaving as an exercise and maybe I'll do it in the assignment. Alright? Now we'll write the equation for Fi. And that case is something very interesting. Particularly, I'm interested in the asymptotic. So, let me take the Hamiltonian Hn for the n particles, which is minus summation I minus 1/2 Li square plus V external Ri plus summation Ij I not equal to j 1 through n 1 over Ri minus Rj. Okay? And since I'm talking about n minus 1 particles, I'm going to split it as minus 1/2 L square plus V external R plus summation I equals 1 through n minus 1 over R minus Ri plus Hamiltonian for n minus 1 particles. Where Hamiltonian for n minus 1 particles is summation I equals 1 through n minus 1 minus 1/2 Li squared plus V external Ri plus 1/2 or the other 1/2 also. Summation Ij I not equal to j equals 1 through n minus 1 over Ri minus Rj. Alright, so I'll split the Hamiltonian like that. And from that I can write the equation for the quasi-particle amplitudes. Is that okay? Any questions so far? Okay. If I take Hn psi n, this is going to be equal to Hn minus 1 plus minus 1/2 L square plus V external R plus summation 1 over R minus Ri I equals 1 to n minus 1. Alright? Acting on summation Fi R psi n minus 1 R1 to R n minus 1. And this left hand side is equal to En Fi psi n minus 1 R R1 to R n minus. All I've done is substituted it in the Hamiltonian and the wave function. Alright? Are you with me so far? Okay. So let's operate this on this. So what do I get? I get summation R is understood. E, this is I. Right? N minus 1 I. Psi n minus 1 I. That's the first term, right? Plus the second term, minus 1 half del square plus V external plus 1 over R minus Ri, sum over I equals 1 to n minus 1, acting on Fi R psi I R1 to R n minus 1 equals En summation R Fi psi I n minus 1. Only substitution. Okay? Now let's multiply both sides by psi n minus 1. Let's say I'm talking about the JF state. R1 to R n minus 1 star dr1 to dr n minus 1. I'm doing that. Okay? Then you can see on the left hand side this term, since I'm integrating only over R1 through Rn, this will give me delta ij. So I get f j E n minus 1 j, first term. Is that okay? Because this too give me delta ij. Right? Plus,
so could you please explain why it is giving you delta j?
because I have, these are the eigenfunctions for the n minus 1 particles. These are the eigenfunctions and they are orthogonal. Right? Okay? Alright. Plus, I have minus half del square plus V external. That's perfectly fine. This acts on Fj. This acts on Fj. Because again I get delta ij. This is R, and this is gives me delta ij. But I have an extra term which is integration psi j R1 to Rn minus 1 star n minus 1 over R minus R I summation. There's too many i's in this thing going on. So let me write the summation k f k psi k n minus 1 dr1 to dr n minus 1. This is summation I equals 1 to n. And on the right hand side I get En. Right, on the right hand side, when I multiply with Fj, again I am going to get delta ij, En Fj. Are you with me on this?
So this last line, summation over n fi psi.
Yes.
First type.
This one?
Yes.
Okay.
And there is fi multiplied by psi I n minus 1.
Right. R1 through Rn minus 1.
Below line.
Yes.
Yeah, this one.
Yeah.
This one.
This is Fi sin I R1 through Rn minus 1.
This is the summation effects on I.
This is summation I.
And here it is fk psi n minus 1 k.
Yeah, I mean, it's an any variable, so it doesn't matter.
So any variable other than j.
Other than J.
J.
J. Is that okay? Okay. So what is the equation for Fj? I get equation for Fj, or Fj, I'm writing this, denominator is minus 1/2 del square plus V external R Fj R plus this term integration psi n minus 1 star j 1 over r minus ri sum over I and all this is equal to En minus 1 j. Is that okay? And I'm going to define. You see, so what we have, this is En. And when I say En, it's the ground state. So we started with the ground state, I'm just in the ground state. And then I have all the energies n minus 1. We always pump in energy to bring in something, right? This is what it is. So this is En minus 1, 0, En minus 1, 1, En minus 1, 2, and so on. Is that okay? Now, Abhishek, to answer your question, if you look at this is if there was no interaction, right? This would be exactly the equation for the orbitals. Because it will be minus 1/2 del square plus V external, Fj equals, a non-interacting system is just the eigenvalue, which is the Fj. So it would be a pure particle. Now I'm calling quasi-particle because now there's an interaction, so kind of gets modified. But the picture is pretty much the same. So I get,
Sir,
yes,
the n minus 1 particle and the one particle that we are separating out, will we see the same external potential?
yes, I'll split that Hr minus 1 is the same external potential, right?
Yes, that's
Why should it be different? Why even the question arose?
That's because if it is outside, there should be some screening.
No, but that screening will come from that Ri minus Rj. I have not left any term in, see, this is one misconception a lot of students, a lot of practitioners also have. They always think put screening, but if I'm writing the exact Hamiltonian and solving it exactly, screening will automatically come in. I don't have to put it in by hand. Right? I mean, where does screening come from? It comes from 1 over Rm minus Rj term. But I'm taking that. Right? So it will come out automatically. Does that answer your question? Okay. So, the equation I get is minus 1/2 del square plus V external Fj plus this term psi n star j is equal to epsilon j Fj, where epsilon j is En minus 1 is the excitation energy. Is that okay? And you can already see what will this energy be experimentally. This is the ionization. So you can see that epsilon 0 will be ionization. Right? Because you remove an electron, you go from ground state of the n particle to ground state of n minus 1. That's the minimum energy required to ionize it. And then if you excite if you take the higher states of the ion, they will be higher. Is that okay? Any questions? Okay. So now we have this equation. Remember, I'm interested in asymptotics. So I'll now go to asymptotic distance. I'll go to R tending to infinity. And since system is finite, all the integration will be the area which is not less than R. So the first term remains the same, minus 1/2 del square plus V external Fj plus, now I can do the expansion. So I'm doing on the side, I'm using the expansion 1 over R minus Rj or Ri is equal to 1 over square root of R square minus 2 Ri dot R plus higher order, which I can approximately write for R going to Z infinity as 1 over R plus Ri unit vector R divided by R square or R cubed. R over R square. Let me see if it is okay. R square will be R cubed. So this will be R. Now R divided by R is R cubed, and I get one more R. Are you with me? Plus higher order, which I am negative. I am keeping only the lowest one. So, if I take 1 over R in this, right? So I am taking 1 over R psi n minus 1j in this summed over will pick up only the term which is jth term, because now I am integrating over everything, right? So I am going to get, and then I sum over I, so I am going to get n minus 1 R Fj. That's from this. I take 1 over R, summed over I running from 1 to n minus 1 gives me n minus 1 over R, and only the jth term gets picked up, and then you get Fj. This is also okay. Plus, I'm going to get expectation value of this, right? Summation, so integration or summation I k psi j n minus 1 R unit vector or I unit vector vector psi n minus 1 k f k 1 over R square. Are you with me on this? This, you know what this is operated for? Dipole operator. So I get equation minus 1 over equals epsilon j minus del square plus V external plus n minus 1 over R and j plus summation over k, the dipole j k f k over R equals epsilon j. That's the equation in asymptotic limit. If there was no interaction, these two terms will not be there. Since there is an interaction, I have this. Fine? You see, Abhishek, this answers your question. Is already seen when charge has gone away. So when you take R to be infinity, electron is already seeing only a charge which is n minus 1. Right? And this term dipole is coming because of the induced dipole. In the n minus 1, this is for n minus 1. Because the wave function for n minus 1. Okay, now we'll argue how things should go. If there were no interaction, then you can see from this equation and the external r tending to infinity went to 0, so everything is going to 0, then you can see that Fj would have behaved like e raised to minus 2 epsilon j. That is because in that limit there is no interaction, so I'll drop these terms. And I'll have minus half del square f j equals epsilon j fj. So that is the asymptotic behavior, if there was no interaction. Is it okay? Now I'll include this term. Now if included, then all fj go as e raised to minus square root of minus 2 epsilon 0. And that will happen. Let us look at this. I can write this as minus 1 half del square plus b external plus n minus 1 over r minus epsilon j fj equals summation k with a minus sign d for n minus 1 jk fk over r square. Fine? Is that okay? Now let me divide by fj on this side. And this k includes k. If fj went like e raised to minus square root of minus 2 epsilon j r, right? Epsilon j is very large, right? And this would have a term, the RHS will have e raised to minus 2 epsilon 0 plus square root of minus 2 epsilon j r, which go to infinity as r tends to. Because this term is larger than this, epsilon 0 is this. Anything else is larger. So this would be positive number. Whereas on the left hand side I'm going to have only finite numbers. This is okay? This is a crucial argument in this. Because all these quasi-particle amplitudes are coupled, right? This happens. So interaction makes each quasi-particle amplitude decay the same constant. So all fj go as e raised to minus the square root of minus 2 epsilon 0. r, which is e raised to minus 2 r, r is fine.
Sir, it is written that if r tends to 0, this term will tends to infinite.
R tends to infinity.
Sorry, r tends to infinity. And if I could write these terms as like root 2 ej minus root 2 ej plus this term, means I will change the signs of.
This is with the minus sign, this comes with the plus sign because I am dividing. And this is larger.
Yes. No, my question is, see, if these signs are changing, then obviously it tends to 0, na?
Why would it tend to 0? This number minus 2 epsilon j is that larger number. Epsilon j is negative. And epsilon j, so let me just remind you, epsilon j is e n minus 1 j minus e n with a minus sign here. It's a negative number.
Okay, that's why it will go.
And if you go to higher and higher steady state, you are larger and larger number. Okay? Alright. So it gets coupled, and therefore first time you're seeing that density goes as e raised to. So density rho, which is mod f j over squared sum over j, goes as e raised to minus 2 the square root of 2 1. It depends on the ionization potential. Is that okay? Any questions on this? Okay, not only that, I can also find from here how fk should go. Now I know that right hand side, so if I behave here of fk as r tends to infinity, so I can write not fj. I can write on the left hand side minus 1/2 del square. As r tends to infinity, I can negate the other terms. Minus epsilon j fj equals, on the right hand side, I can just keep the first term d j 0 f 0 over r squared. Why I am keeping only that term? Because all the terms are going as exponential, so I am just keeping the exponential term. The behavior will be like fc. Right? And fj just goes as, so this becomes epsilon 0 minus epsilon j, goes as the minus sign dj 0 f0 over r squared, and therefore fj will go as dj 0 over epsilon 0 minus epsilon j r squared. So compared to f0, the square by the smaller by 1 over r squared, and higher up you are, the energy is smaller, the amplitude by that energy difference. And now the next thing I'll leave for you, from this you can show how the exchange correlation should go. If we go to r tending to infinity, Bourne-Chack equation is minus 1/2 del square plus v external plus v Hartree plus v exchange correlation phi I, so I'll take phi max equals epsilon max. It doesn't actually matter, phi I. right? And whatever else is left, so this will go as minus 1 over r, that will come from here. Okay, because in that limit, you see, F0 behaves, F0 determines the density, so does phi, or phi max, right? Because far away, E max is the largest. Far away, only phi max dominates. And the last term here, and this comes out to be minus alpha over r raised to 4, where alpha is the dipole polarizability of the ionic ground state. And you can see this is the dipole moment. Finally, you can, and there is this through perturbation theory, if you calculate the dipole moment, they'll have a term epsilon 0 minus epsilon j. They'll have, because that's what comes in the first order change in the wave function. This is the dipole moment expectation value, so you can show this. Okay, this comes from a change, and this comes from correlation. I'm going to see if there are any questions. So you see, this is a mixture of DFT and many body concepts. You're defining a quasi-particle amplitude. In the limit of phi going to infinity, it becomes same as F0. F0 becomes same as phi max, and through that you can relate here. Any questions?
So in GIST, what we did is we divided the Hamiltonian into two terms. First one is single particle, another one is n minus 1 particle.
That's right.
And then we have approximated 1 by r minus r prime.
Because I'm going to the r equals infinity limit.
We did a multiple extension and we took up to the second order term.
Yes.
This is the dipole term.
Yes.
Right. So after that, I was a little lost. I mean, what exactly are we doing?
No, probably you lost a lot. I took the whole thing. I don't want to repeat it, so you have to ask me a pointed question. After that, all that I did was the manipulations with different terms, came up with the dipole term, wrote the equation for the quasi-particle amplitude, and then just kept looking at how everything will behave. And I showed you each quasi-particle amplitude because the interaction term will decay in the same manner, corresponding to the lowest eigenvalue in magnitude, and then get a behavior of the J quasi-particle, and J obviously is not equal to 0. And you can always shift the origin to make the first dipole, not induced dipole 0. Okay? Given you the reference, I've gone through all the key steps. Now you have to put in some effort yourself. Alright? Okay. So that was one part. Now notice out here, we're looking at exponentials and we argued to the exponentials that how each f naught is going to behave the same way. Now I'm going to look at another equation, which is the equation for not quasi-particle amplitude, but density amplitude. Prove the same thing to that, and that also connects with orbital free DFT. Equation for square root of rho. So I'm going to define something called the density amplitude. Through this equation. If I have a particle function, I'm going to write this as square root of rho r over n phi n minus 1 kind of depends on r in a parametric way. And if you look at phi n minus 1, then mod phi n minus 1 square gives the probability of finding electrons at R1 to R n minus 1 for nth electrons at R. Because this mod square gives you the probability of finding a particle at R1, R2, R3, R4, R2, Rn. Rho r by n, if I take mod square, it will give me the probability of finding a particle at R, and the rest is left is where are the other particles. So that's why it's known as density amplitude. Alright? And what we are going to do is write an equation for square root of rho using density amplitude. Okay. So for that, first I'll have to prove that I'll not prove, I'll ask you to prove it. 1 over this root rho square over root rho is equal to integration rho n over 2 rho r psi n star del square psi n, and I integrate it only up to, I'll write it only once, dsn and dr1 to drn minus 1. You can see I'm getting a function of r here, so it has to be integration only of the rest of the variables. And last one is this r1 to rn minus 1 plus 1/2 integration del phi n minus 1 r1 up to rn minus 1 r mod square of d s1 ds2 dsn dr1 to rn minus 1 ds1. Let me see if I've gotten all my factors right. Yeah. To prove this, what you should do is calculate del phi n minus 1 mod square ds n dr1 to drn minus 1 ds1 to dsn minus 1 integration. Do this and rearrange. Okay, then you can show this. Now what we do is, we again do the same trick as we did earlier, and we will write Hn, which is equal to minus 1/2 del square plus b external plus summation I equals 1 to n minus 1, 1 over r minus ri plus h n minus 1. Now I'll do a manipulation which is the other way. And the other way manipulation is going to be, I'm going to write 1/2 del square equals minus hn plus hn minus 1 plus all these terms. Is that okay? Some manipulations.
Why are you writing dsn separately from
Well, I just want to show that I'm doing the spin integration also. I'm going to drop it from now. I'm summing over the spin also, all possible spins. All I'm just doing the space value.
That's equivalent to ds1 dot ds.
Yeah, this is not together. Alright? Now when you do this, you substitute for hardware square here. If you substitute for hardware square here, you can already see that minus Hn, so I'm going to get, you substitute this here, I connect these two. Alright? So you can see I'm going to get 1/2 del square root rho over root rho, that is on the left hand side, is equal to n over 2 rho r. First term, hn x on this gives you en, right? So you're going to get minus en psi n star psi n integrated over all this. Then I'm going to get hn minus 1. Hn minus 1 is going to act on psi, it will act only on phi n minus 1. So then next you want to get plus rho r over n, this is n of phi n minus 1, hn minus 1, phi n minus 1. That's the second term. Third term, you want to get some V external R psi n star psi n, all this label. And fourth term is this. Are you with me? Do you follow the steps? Right? Once I do that, and then do all the manipulations, what you get is this equation. You get the equation minus 1/2 del square plus V external R plus some V effective on acting on root rho equals mu root rho, then mu is minus R, which is E, and minus 1 minus E. I had done one manipulation in all this. I had subtracted minus E and minus 1, which I can always do a constant to add it to C. That's how I put it very easy. So that manipulation, maybe 2-3 steps I'm leaving for you. Alright, where V effective comes out to be integration rho n minus 1 r prime over r minus r prime dr prime plus phi n minus 1 h n minus 1 minus e n minus 1 phi n minus 1 plus integration mod phi n minus 1 square ds dr1 dr n minus 1, and again ds ds. So I define V effective, and you can see Abhishek again, V effective comes out to be the Coulomb potential into n minus 1 particles. Somehow it's taking interaction into account. equivalent to. I don't have to say very, it's equivalent to. And I'll show you again what you were doing yesterday. If I wrote my E0 as 1/2 del square del root rho square plus E rest, which I'll call E Pauli, plus E external plus E R3 plus E XC, and I minimize E with respect to rho. Alright? So instead of minimizing with respect to rho, I'll minimize with respect to root rho. I can always do that. Consider all this as a function of root rho. Root rho is another function, which is non-zero. Then you get precisely this. You get minus 1/2 del square plus V Pauli plus V external plus V R3 plus V XC V Pro mu. These two are the same equations. And you can now see that we have written an expression for these three terms. This together with this together with this, we are calling V effective R. So we have gotten an expression for V Pauli plus V Hartley plus V exchange correlation in terms of a many-body wave function. If you have a many-body wave function, you can calculate these terms. There's a little trick. You have to do an iterative process, but we've written that. Again, the connection between a density equation and a wavefunction equation. I'll use this now to prove again that the density will decay as e raised to minus 2 to 2i now.
So E rho is equal to half grad root rho square plus
Which
middle
one?
column. Middle column.
This one,
Middle column.
this one,
Uh,
or this one.
yeah, the top equation.
Yes.
Yeah. So the first term is basically the 100.
This is 1 by. If you take grad of this, what do you get? You get 1 over root rho,
Root rho, grad rho.
grad of rho. And you square it, grad rho square, grad rho.
And the next term E Pauli contains
All the rest.
all the
Thomas Fermi, whatever. Thomas Fermi is an approximation to E Pauli, but the energy goes up, right? Compared. So that's what you were talking about yesterday in your soda. That's E Pauli. Okay? Anything else? Anybody else have any question? Okay. Now that.
So we started with half grad square and operated on root rho, right? That equation, the first equation that you have.
This is derived.
So from there,
No, I'm connecting the two.
you are connecting.
Okay. Now you notice that P effective is always greater than or equal to 0. Why? This term is positive. Hn minus 1 minus En minus 1, phi n minus 1. Phi n minus 1 is not necessarily the wave function for the n minus 1 model. So this by radiation principle is going to be greater than 0. Expectation value of Hn minus 1 with respect to this is going to be greater than the downstream energy. And this term anyway is positive. So this is greater than or equal to 0. So if I look at this equation, minus half del square plus V external R plus V effective root rho equals mu root rho, right? and let, as r tends to infinity, let the external go to 0, right? And let, I mean this is known, that rho goes as e raised to minus some 2 alpha r. Okay? Then I'll have 2 alpha, or root rho, so alpha plus V effective equals mu alpha is equal to mu minus V effective. Mu is negative, V effective is negative, so this is mod alpha is greater than.
So V effective is equal to V Pauli Vx plus V exchange. So is this equation is comparable to that?
This is exact, yeah, this is an exact expression in terms of the wave function, many particle wave function.
Okay, so this Hn minus 1 and Dn minus 1 term, so is it equal to the V exchange?
No, Hn minus 1 and En minus, this is just the expectation value of Hn minus 1 minus En minus 1. With respect to some n minus 1 particle wave function, this is necessarily greater than or equal to 0.
Yeah, this is greater than equal to 0. So my question is that is this equation or this value V Pauli and these three terms sum,
They have to be the same.
they have to be same.
Yes.
So can we compare these three values with these values? Like V Pauli is equal to this one?
No, you can't. They're all mixed together. You can't separate it out. You have to write an expression of V Pauli which you subtract. And V Pauli is, remember, this is non-interacting kinetic energy, so it's written in terms of Moncham orbitals.
Yeah, so basically these two values are equal but the terms are not.
Which are different terms, I don't know.
Yeah.
Right? That one has to develop a technique to do it. Okay. So, what this says is that density, that means rho, decays faster than e raised to minus 2. Okay? Because this comes out to be this. Value is larger. Okay? So now I'm going to show you, go the other way. Now, under what circumstances can this be equal? If, as you go far away, as the electron goes far away, if phi n minus 1 collapses to psi n minus 1, if as r tends to infinity, phi n minus 1 goes to the exact psi n minus 1, then this will go to 0, right? And this anyway, as r tends to infinity goes to 0, right? And this is the magnetic energy density for psi n minus 1, that also decays exponentially. So, in that case, it may be equal. V effective equal to 0, otherwise it is 0. Now what we show is that the other way also is satisfying. And that will show you if alpha is greater than faster than. Okay.
Shouldn't it be less than
No, mu is negative.
mu is negative?
So far I've been saying mu is minus I. Mu is minus I, so it's negative. And V effective is greater than 0, so this whole thing is more negative. Okay, now I'm going to argue the other way. If I look at H psi n,
So
right?
if
Yes.
V effective is greater than 0, so it means we are subtracting some negative value, na?
From a negative value, suppose this is minus 5, so you are making minus 5.2, minus 5.3, which is in magnitude greater than 5. This is also negative.
Okay.
Mu is always negative.
They are additive.
They are additive, yeah.
Okay, magnitude. Yeah, so there is also something.
Suppose I take Hn psi n equals En psi n, and I multiply by psi n minus 1 star and integrate ds and dr1 to drn minus 1. Integrate psi n minus 1 star and all that. Okay? Then you can get an equation, right? You get an equation for square root of rho phi n minus 1, where phi n minus 1 is the density amplitude, times psi n minus 1, where psi n minus 1 is the ground state for n minus 1 particles. Alright? Again, manipulations along the way. And what are the manipulations? You will again write Hn as Hn minus 1 plus the rest of the terms, and Hn minus 1 can act on the left hand side, give you En minus 1. Alright? On the right hand side, you will get some term, whatever, right? I mean, this you can write as, here also you get integration root rho over n phi n minus 1 psi n minus 1. Alright? So you multiply and do all this. So you find out to get an equation for this. And the again, if you do all the manipulations in the large limit, what are you going to get? Is an equation, alright, which looks like this. And the limit of large r as r tends to infinity. Do this, and the equation you get is minus 1/2 then square plus the external goes to 0, alright, and rho n minus 1 will go to 0, you're going to get this quantity I'm going to call G, as the book calls it, the paper calls it. G for the ground state is equal to mu. Okay, because along the way, there are plus terms, the effective G plus n minus 1 over Rg plus some term, which all goes to 0 as R goes to infinity. Okay, so that manipulation I'm giving to you. I'll give you the difference. And once you do that, what are you going to get? And this is again a beautiful argument. You're going to get that square root of rho phi n minus 1 psi n minus 1 goes as e raised to minus square root of minus 2 r as r tends to infinity. Okay? Now phi n minus 1 psi n minus 1 Schwartz inequality, easiest way to do is A dot B is less than or A. And therefore, root rho times this will decay. Okay. So if root rho goes as e raised to minus alpha r, then e raised to minus alpha r times the quantity as r goes to infinity, which is less than 1, goes at e raised to minus 2 mu r, then alpha has to be in magnitude less than equal to square root. Because this multiplied by something else is equal to this. Now I found alpha is less than this, here alpha is greater than this. Another factor of 2 missing. And these two together imply that alpha is equal to square root of minus mu, which is the square root. This is one of the most cited papers, and this is AB. Purdue, Sani, PRA, I think 1984. Okay, so when we took the quasi particle amplitudes and showed you that the density can go like that, when we are taking the quasi, not the density amplitude, here we are not considering any exponentials, sum of exponentials or anything, straight away showing that it should go as. Okay? And finally, just one more point. So read that paper, I think I have given you enough, so you can follow this paper very easily. Finally, as Dimple was asking, you have the effective equals V Pauli plus V Hartree plus V exchange correlation. And this we have written in terms of psi n, right? So I can always calculate this quantity. And if I subtract V Pauli, and from this I can also calculate the density V Hartree, I can get the exchange correlation. So from a wave function I can get an exchange correlation directly. Except that I don't know what V Pauli is corresponding to this particular density. So what you do is, you start with the Kohn-Sham equation, V external plus some approximate equation from which you calculate V Hartree, you can anyway calculate some VXC in the ith iteration. Get some phi in, okay? Phi j was epsilon j phi j. Calculate V Pauli, right? And this gives you phi j. Get V Pauli. And from this, get VXC, check for self-consistency, and go back. So you complete the cycle until you come up with same thing, phi j starts coming back. So you have found from a wave function the exchange correlation. This has become, I mean, I've given it in a very simple form, people have derived it in a different way, and there's something called the RKS, Taylor method, and they made really big to do about this, and we've shown that this comes from LBS equation, from the expression in terms of density, amplitude, and just do it correctly. Okay, thank you very much. I'll stop here.